In this segment, we'll talk about Riemann sum for numerical integration. So this is something which you have already done in your integral calculus class. So we're going to just review it so that you get the feeling that, hey, that when we're talking about exact integration, that it did come from some kind of a numerical integration in the first place. So we'll talk about the Riemann sum here. And just to keep things straightforward, we'll only talk about the left-hand Riemann sum. So in this left-hand Riemann sum, if we are going to, let's suppose, integrate a function from, let's suppose, from a to b, we want to be able to do that. So we want to be able to find out what the value of this integral is by using Riemann sum. We'll be able to only find an approximate value if we use the Riemann sum with only finite number of rectangles. So the left-hand Riemann sum starts from here, then it will keep on going, and the last one will be right here. So we'll be finding out what the areas of these rectangles are, add them up, and that gives us an approximate value of the integral. So let's suppose if we call this to be x1, we can call the next one to be x2, next one to be x3, this one to be xn, and the last one to be xn plus 1. So basically your x1 is a and your xn plus 1 is b. Now keep in mind that these particular widths of these rectangles, they do not necessarily need to be the same size. So let's suppose this is delta x1, this is delta x2, and this is delta xn are the widths of these rectangles right here. And what the Riemann sum basically tells you is that S is equal to f of x1, that is the value of the function at this particular point, times delta x1, which is the width of the rectangle. Then the next rectangle will be the height of that rectangle at this particular point multiplied by the width of that rectangle. And if you look at the last one, it'll be f of xn times delta xn. So bottom line is what you're getting is the summation of f of xi times delta xi going from 1 to n. If we want to be able to translate this into an exact value of the integral, what we have to basically say that f of x dx will be this summation, that is the addition of all these rectangle areas, but the limit of course will be that delta xi will be approaching 0. So the magnitude of delta xi has to approach 0, and if we get infinite rectangles, and once we get infinite rectangles, that itself will be the exact value of the area under the curve. Let's look at an example now. So the example is here. It says use the left-hand Riemann sum to approximate this particular integral, and you got to use 3 equal segments. So what that means is that we have 5x squared right here. And what we want to do is integrate from 3 to 9. And we want to make 3 equal segments. And of course we're using left-hand Riemann sum, so that means we start from the left here. And we have 3 rectangles right here, guys. And we are saying 3 equal segments. So if it is 3 equal segments, that means h is equal to 9 minus 3, which is the width, which is b minus a, divided by 3, and that gives me 2. So the width of each segment here is 2. This one is also 2, and this one is also 2. So if we look at the area under the curve based on these rectangles, it'll be the area of the first rectangle, area of the second rectangle, and area of the third rectangle. The first rectangle will be the value of the function at 3 times 2, which is the width of the rectangle. The area of the second one will be f of 5 at 2, because you can see that since the width is 2, this is 5 and this is 7. And the third rectangle is the value of the function at 7 multiplied by the width, which is 2. The value of the function at 3 is 5x squared. The value of the function at 5 is this. and the value of the function at 7 is 5 times 7 square, of course multiplied by 2 because that's the width. And if you calculate this value, it turns out to be 830. The exact, of course, is 1170, but you will be able to achieve that particular exact value only after you have infinite rectangles to approximate the integral. Here we have only 3 rectangles, and you at home can say, hey, let me use equal 4 segments or 5 segments or 10 segments, and you'll see that, hey, your answer will get closer and closer to the exact value. So one of the things which I wanted to emphasize here was that you have already been introduced to numerical integration in your calculus class. So as much as we like to think that exact integration comes before numerical integration because that's the way it is taught in the course curriculum, but it's the other way around. The numerical integration precedes our exact integration, but we have to not reinvent, I should say, but readdress the things which you have learned in your calculus class so that we can talk about some of the more complex numerical integration techniques which give us more accurate results quickly. And that's the end of this segment.